Welcome to this session. Now we are basically looking into the modeling of gel layer controlling filtration in a rectangular channel with there is a two-dimensional model with growing or developing mass transfer boundary layer. Now, as we have seen earlier, we have already determined the concentration profile, and now we will be evaluating the various derivatives of the concentration profile. So, del C star del x star will be nothing but 2 C g star minus 1 d del star dx star y star by del star square minus y star square by del star cube, and I am just omitting a step and writing the final expression, and del C star del y star will be 2 C g star minus 1 minus 1 by del star plus y star by del star square, and del square C star del y star square will be 2 C g star minus 1 over del star. Now, we substitute all these derivatives in the governing equation and see what you get. 3 by 16 Reynolds Smith d by L d delta star dx star. The reason y star should have been multiplied with that. So, we will be putting into that 2 C g star minus 1 y star square by del star square, because there was a y. So, it will be multiplied with this minus y star cube by del star cube minus p w by 4 del C star del y star. So, 2 C g star minus 1 minus 1 by del star plus y star by del star square is equal to del square C del y star square. So, it will be 2 C g star minus 1 del star. So, 2 C g star minus 1 will be cancelling out from all the sides, and what you will be getting, let us say this is A. Okay. A is equal to 3 by 16 Reynolds Smith d by L. So, A d delta star dx star y star square by del star square minus y star cube del star cube minus p w by 4 minus 1 by del star plus y star by del star square is equal to 1 over delta star. So, we multiply both sides by dy star and integrate across the boundary layer thickness 0 to delta star, and see what we get. So, this will be obtained that E A d delta star dx star. Since delta star is a sole function of x star, the derivative will be sole function of x star, and it will be out of the integral sign. And if you really do that, it will be 1 by 3 minus 1 by 4 minus p w. So, there will be delta star there. So, delta star by 3 delta star by 4 minus p w by 4 minus half minus 1 and plus half y star square by 2. So, del star will be cancelling out. So, this will be the 1, and it will be delta star by delta. So, this will be 0 to delta star. So, you will be having a delta star there. Okay. Yeah, delta star there. Now, and since there will be a square, so there will be 1 delta star on the right hand side. Now, after this, what we will be getting is A delta star A by 12 delta star d delta star dx star plus p w by 8 is equal to 1 over delta star, and ultimately you will be getting A by 12 delta star square d delta star dx star plus P w del star by 8 is equal to 1. Now, let us look into the. So, this will be the form of the governing equation that one will be getting after this. Let us look into the boundary condition at y star is equal to 0. So, we have already seen that P w C g star by 4 plus del C star del y star will be equal to 0. So, we have the expression of del C star del y star and put it there. So, this becomes 1 by 4 P w C g star minus 2 C g star minus 1 by del star will be equal to 0, and ultimately you will be getting P w del star by 8 is equal to C g star minus 1 divided by C g star. So, once you put this P w delta star by 8 here, and finally, you will be getting a by 12 del star square d del star dx star is equal to 1 minus C g star minus 1 by C g star, and C g star will be cancelling out, it will be getting 1 over C g star. So, this can be integrated over length. So, a by 12 delta star square d delta star from 0 to delta star and 1 by C g star dx star from 0 to x star. That will be giving me an expression of delta star as a function of x star. So, this becomes a by 12 delta star by delta star cube by 3 is equal to x star C g star, and you will be getting delta star cube is equal to 36 a C g star to the multiplied by x star, and one will be getting an expression of delta star as 36 by a C g star to the power 1 upon 3 x star to the power 1 upon 3. That is how the delta star, the mass transfer boundary layer is varying as a function of x star. And if you remember, the functional variation of mass transfer boundary layer thickness in case of osmotic pressure controlled filtration is also del star as a function of x to the power 1 upon 3. So, next we will be looking into the permeate flux expression of the permeate flux. P w will be, if we remember, P w is nothing but C g star minus 1 divided by C g star multiplied by multiplied by 8 into delta star. So, we are going to put the expression of del star there. So, 8 C g star minus 1 divided by C g star, and del star 36 by a C g star to the power 1 upon 3 x star to the power 1 upon 3. So, in fact, if you remember the expression, it was P w delta star by 8 is equal to C g star minus 1 by C g star. So, we have put what is the expression of P w? P w will be nothing but 8 by delta C g star minus 1 by C g star. So, delta star will be in the denominator. So, this will be delta star will be in the denominator. So, there will be a minus 1 upon 3 and there will be minus 1 upon 3 here. So, we will be getting 8 C g star minus 1 divided by C g star a over C g star divided by 36 to the power 1 upon 3 and x star to the power minus 1 upon 3. This is how permeate flux, non-dimensional permeate flux is varying as a function of x star. We can integrate it out. If you can integrate it out, the length average permeate flux will be given as P w x star dx star 0 to 1, and integration all this will be constant, and integration of this will be giving you a value of 1.5. So, 1.5 should be multiplied by 12, 1.5 should be multiplied by 8 and it will be returning a value of 12. So, 12 by 36 to the power 1 upon 3 a to the power 1 upon 3 and c g star to the power 1 upon 3. So, this will be c g star minus 1 divided by c g star to the power 2 by 3, 1 minus 1 upon 3 is 2 by 3. So, we are almost close to the expression of length average permeate flux. So, P w bar is equal to 12 divided by 36 to the power 1 upon 3, A is 3 by 16, 1 upon 3, Reynolds Smith d by L to the power 1 upon 3 and c g star minus 1 divided by c g star to the power 2 by 3. So, it will be c g star to the power 1 upon 3 minus c g star to the power minus 2 by 3. Now, for the limiting case under certain, so this will be the expression of P w under certain case c g star, we can write c g star to the power 1 upon 3 is equal to exponential ln c g star to the power 1 upon 3. So, that gives me exponential 1 by 3 ln c g star, and if this becomes less than 1, then we can have an exponential expansion. So, and neglecting the higher order terms 1/3 ln c g star. If c g star ln c g star to the power 1 upon 3 is much less than 1. So, that means c g star should be much less than e to the power 3. So, that will be around 20. Okay, that will be around 20. So, similarly c g star to the power 2 by 3 can be written as exponential minus 2 by 3 can be written as exponential ln c g star to the power minus 2 by 3, and we will be having 1 minus 2 by 3 ln c g star. So, P w bar will be nothing but 12 by 36 to the power 1 upon 3, 3 by 16 to the power 1 upon 3, Reynolds Smith d by L to the power 1 upon 3, and this minus this, or this minus this, 1 minus 1, it will be cancelling out, 1/3 minus plus 2/3. So, it will be 1 only. This becomes ln c g star, that is c g by c naught. Now, if you really calculate this numerical value, the numerical coefficient, this turns out to be 2.08 Reynolds Smith d by L to the power 1 upon 3 ln c g by c naught. Okay. So, what will be this? This will be the Sherwood number or length average mass transfer coefficient is 2.08 into Reynolds Smith d by L, and if you remember to the power 1 upon 3 for the case of the laminar flow, if you remember for the Levex solution, we have SH is equal to 1.85 Reynolds Smith d by L to the power 1 upon 3. So, whenever we will be considering a developing mass transfer boundary layer, there will be around 12% enhancement of permeate flux one can expect out of the system. So, that completes the modeling of gel layer control filtration. In the next we will be moving over to the module design. So, we have looked into the details of the osmotic pressure control filtration, we have looked into the details of the gel layer control filtration. Then one more model I think I should touch over, that will be the resistance in series model. So, in case of resistance in series model, so this is nothing but a phenomenological equation. We assume that permeate flux is equal to driving force divided by all the resistances that we have put into series, absorption resistance plus concentration polarization resistance. So, all these resistances are put into series, but this is entirely an empirical model. So, what is done here, this is generally we take recourse to the empirical models like resistance in series model in case where there will be having a complex real fluid, for example, like effluent or a juice or a very real life effluent which will be containing thousands of components. As we have discussed earlier, it is difficult to identify these components. Not only that, it is difficult to identify their concentration as well as their property. So, it is better to measure the permeate flux at every time point and evaluate these resistances. In fact, there are ways to measure these resistances, and then you for example, if you would like to have a two resistance model, that is membrane resistance and polarization resistance. So, it is very easy to find the membrane resistance, because we can know, we have already seen we can independently find out the membrane permeability, where from the permeability data we can get the membrane resistance. And from the permeate flux data, if we measure if we conduct an experiment and record the permeate flux data, then from at every time point we can calculate the what is the polarized layer resistance, because we know the operating pressure, we know the membrane resistance, we have the experimental flux data. So, we can calculate the what is the polarization resistance every time point. So, that will be nothing but mu Vw, which will be function of time minus Rm. So, we will be getting the R polarization layer resistance every time point, and then we will be getting these values of the polarization resistance for different operating pressure and operating time. Then we evaluate a relationship between the polarization layer resistance with the operating conditions. Once that is done, then we can put back that expression into this model, and this can be used as a these will be validated for a over small range of operating conditions. Then this can be used as in the predictive mode for different operating conditions for the same complex fluid. So, absolutely complex fluids where it is very difficult to understand or estimate the properties, streams, components, their concentration, etc., then one can take recourse to the resistance in series model. Okay. So, we have looked into the various types of models, and then we will be moving into the modeling of membrane modules. Membrane modules. So, what are the modules? So, as we have discussed earlier, the membrane modules are basically the housing of the membrane, and all these membrane operations are occurring under high pressure. So, there is a housing of the membrane that is very required, and membrane housings are really complicated. There are some well known modules. This membrane housings is known as the module. The well known modules are plate and frame module, plate and frame. Secondly, the spiral wound. Third one is tubular. Fourth one is hollow fiber. I will just discuss about them. Plate and frame is basically the module where there will be the plates will be held between the frames, and membrane will be held to the plates by the frames, and across the plate there will be two surfaces, and one can put two membranes either in the circular disc or maybe rectangular in shape. Such plates and frame arrangement can be kept one after another in the module and can increase the surface area. That is number one. In case of spiral wound module, a sandwich of membrane support system will be spirally wound across a central rod, and there is a very complicated special arrangement, and then this whole thing can be glued to the internal rod, and then it will be done. In case of tubular module, the module is in the form of a tube where the internal surface of the tube is basically especially wound by a membrane. So, it is called a tubular module. And in case of hollow fiber modules, there are fine hollow fibers which will be having internal diameter 400 to 500 microns or even slightly higher, and these hollow fibers will be packed in a bigger fiber, and one can get large number of fibers packed in a bigger diameter pipe, and then one can realize a huge surface area even in a small volume. What is the diameter of the filtration area? What is the filtration area in these hollow fibers? If the diameter is d, the filtration area is pi dl. If n number of such fibers are packed in a bigger tube, then we will be having a total surface area, total surface filtration area is n pi dl. So, although the diameter is less in number, but for example 400 micron, 500 micron, 600 micron in that range, but the number is very high, let us say around 10,000, 15,000. If we really pack such huge number of fibers in a bigger tube, then we can realize around 1 meter square, 2 meter square area in a small volume. So, therefore, the idea of every module is to get the maximum filtration area or surface area in a small volume. So that the design of the module will be very compact. Now, there are two types of analysis are required in order to design these modules. one is the flow through a rectangular channel and flow through a tube. If we consider a flow through a rectangular channel, that will be closely resemble case 1 for the Platon frame and case 2 the spiral wound module. That means, if you open up the spiral wound module, it will be like a flow over a flat sheet. Now, for the flow through a tube will be resembling to the tubular module and the hollow fiber module. Now, let us consider the Newtonian fluid, Newtonian laminar flow through rectangular channel, and we will be again doing a very simplified case in the beginning, then we will build up the case and going to the more realistic case or complicated case at the end. Okay. So, first case will be the will be doing an analysis for the spiral wound module. So, it is basically flow through a rectangular channel where the membrane is present on the both top and bottom surface of the channel, and case 1 will be considering the permeate flux is constant. Okay. So, let us consider a membrane channel where this is the middle of the channel of half height h, this q in total volumetric flow rate inside towards going inside the channel, and this q out, that is going out of the module, this x equal to L 0 and this x equal to L, length L is the length of the channel, and we will be considering a constant permeate flux in the module. So, all these are constants. As we have also discussed earlier, that velocity in the retented velocity in the flow channel will be in the order of meter per second, and the permeate velocity will be in the order of 10 to the power -5 to 10 to the power -6 meter per second. So, there is at least 5 or 6 order of magnitude difference between the permeate flux and the retented flow rate. So, therefore, we will be assuming the laminar profile, that is the parabolic velocity profile that is existing inside the channel will be remaining undistorted by the permeation at the wall, because it will be at least 5 to 6 order magnitude less than the bulk flow. If we really do that, then we can write down the famous law of volumetric flow rate under laminar flow condition through the channel, that will be 2 h cube w by 3 mu times d minus dp dx, and h is the half height, mu is the viscosity of the solution, w is the width of the channel. Now, we can see that what is P? P is the pressure, this dp dx is the axial pressure drop. So, dp dx is the axial pressure drop, and let us see what is dp dx. This is basically this P can be written as P upstream. So, what is P transmembrane pressure drop? P transmembrane pressure drop is nothing but P TMP is nothing but P in the feed side minus P in the permeate side. So, that is the atmospheric pressure. So, this P is the same as this P. So, d P transmembrane pressure drop dx will be nothing but dp dx, because P atmosphere is constant. So, what is dp dx is saying is the same as the d transmembrane pressure drop dx. So, we assume dp dx d delta, so the same as d delta p dx, and P transmembrane pressure drop is nothing but delta p. So, dp dx will be treated as d delta p dx. Okay. So, this will be at any point of time. So, this will be absolute pressure at any point of time. Okay. Once we identify this, we can write down the solute total overall material balance in a differential area, in a differential element of the channel. Suppose this is the channel and this is we are talking about a cross section located at x and another cross section which is located at x plus delta x. Okay. So, total material going into the system, total material going out of the system, and total material going out of the wall because the membranes are there. So, rho, so this is q at x, this is the volumetric flow rate q at x plus delta x. So, rho times q at x minus rho times q at x plus delta x, that is going out, minus rho permeate V w 2 w dx is the this differential area. W is the width in this direction normal to the plane of the paper, and this is delta x. Okay. So, 2 w dx, there will be two surfaces, that is why the 2 is appearing, is equal to 0 at steady state. Now, what it will be giving you? This will be giving you minus dq dx is equal to 2 w V w. So, this equation will be giving you a governing equation of how q or volumetric flow rate is varying as a function of x in a membrane module, in an actual membrane module. Now, we have written that q is equal to 2 h cube w over 3 mu minus d dp dx will be d delta p dx. So, just differentiate it once more time with respect to x, will be giving you dq dx is equal to 2 h cube w by 3 mu minus d square delta p by dx square. So, you equate these two and you will be getting the governing equation of pressure drop across the channel is equal to dx 3 mu V w by h cube. This gives the governing equation of delta p across the channel. This is a second order ordinary differential equation, and you need to specify two boundary conditions to solve this problem. One boundary condition is at x equal to 0. We know the delta p inlet, delta p is equal to delta p in, that is known to us, and at x is equal to 0 we know the volumetric flow rate that is going into the system. So, d delta p dx is known to us, because d delta p dx will be known to us minus 2 h cube w 3 mu is equal to q in. So, these two conditions are known to us. So, if you remember that these two conditions are specified on the same boundary, so this is known as the Cauchy boundary conditions. So, using these two conditions, this equation can be solved, and once this equation will be solved, you will be getting a solution of pressure drop across the channel. If you really solve this equation, this is straightforward, everything is constant on the right hand side, substituting the boundary condition, ultimately you will be getting a solution delta p I is equal to delta p x, okay, delta p I in minus delta p at any x location is equal to 3 by 2 mu h cube w q in x 1 minus 2 V w x V w w times x divided by 2 q in. So, why we have put in this form? Because that will be giving you what is V w w x, because 2 V w w x will be giving you what is the total recovery. So, F is the fractional recovery of the feed in the filtrate or in the permeate, fractional recovery of feed. So, that will be nothing but 2 w at x equal to L times V w divided by q in, that is gives you total recovery of the feed that is coming into the permeate. So, we have to maximize this. So, it is basically at x is equal to L will be at the end of the module, delta p in minus delta p L is equal to 3 by 2 mu h cube w q in L 1 minus f by 2. So, this is the pressure drop across the channel, and then this according to this pressure drop one can select a pump, so that this much pressure drop in the module will be sustained by the pump. Similarly, the same expression we can do the similar type of analysis in case of a flow through a tube. For the tubular module, we can get the expression of the pressure drop, and the expression of the pressure drop will be similarly delta P in minus delta P L is equal to 8 over pi mu by r to the power 4, where r is the radius of the module, as q I times L 1 minus f by 2 pi, where f is the fractional recovery, it is 2 pi r L V w divided by q I. So, total surface area is 2 pi r L, and that will be multiplied by V w permeate flux. That will be the total amount of flow rate that is obtained in the permeate divided by total permeate flow rate going into the system, that will be the fractional recovery. So, in the I stop in this class. In the next class, what I will be doing, I will be going for one more step of complication, that is I will be considering that osmotic pressure is negligible and V w is equal to L p del p. That means permeate flux is proportional to delta p. In the then I will be considering another case, the most realistic case, that is the V w is equal to L p into delta p minus delta pi, and then we will be looking into the how to do the module design in that case. Thank you very much.